Alright, tonight's video we'll look at gravity and inertia. So we're going to answer why you don't go flying into space on your own and why the Earth doesn't crash into the sun and get pulled in by the sun's gravity. So we're going to start with gravity. Alright, gravity is what we call a universal force in science. So it exists all over the universe as far as we can tell. We've never seen any evidence that any parts of the universe don't obey the rules of gravity. So gravity is a force that pulls all objects with mass towards each other. All right, we think of it as just being like the Earth pulling us down, but you have gravity. The Earth has gravity, the sun has gravity, your pencil has gravity, the laptop you're watching this on has gravity. Literally anything that has mass has gravity. All right, so you're going to take your own notes for this section. Right? And the strength of that gravity depends on two things. The distance between two objects, so two objects that are closer together are going to have stronger gravity, and the object's mass. Larger objects have much stronger gravity. Right? So if we think about that, right, the sun is way bigger than the Earth, so it should in theory have stronger gravity, but it is also obviously way farther away from us than the Earth is. So distance is a much more important factor in gravity. So even though the Earth is millions of times smaller than the sun, it is also millions of times closer, right? It's right under our feet. So the Earth's gravity is much stronger than the sun's gravity, right? On the other hand, your laptop is really close to you right now, but it's so small compared to the Earth, right? It is trillions or quadrillions of times smaller that its gravity is effectively nothing. Alright, and this diagram just kind of shows how this works, right? Force of gravity acts between all objects, tries to pull them together. If mass increases, the force of gravity increases. And if distance increases, the force of gravity decreases. Alright, so this might be a good diagram to kind of sketch into your notes that would help you kind of visually illustrate how these things work. So if all this is true, why doesn't the Earth fall into the sun, right? The sun is pretty massive, right? Even though it's really far away, eventually, in theory, its gravity should be enough to pull the Earth in and we should all die a flaming, horrible death. Fortunately, that doesn't happen. And it's because of this thing called inertia. So inertia is the tendency of an object to resist change. So that's kind of a weird kind of scientific definition. What that means is tendency of an object to resist change. What that means is an object wants to stay put if it's stopped and keep moving in the same straight direction if it's moving. All right? So what this means is we want to stay put if stopped, keep moving straight if moving. Right, which means to turn is going to require some extra energy, some extra force. Right? So we'll do some demos in class tomorrow, but if you're sitting in a rolly chair, for example, a chair with wheels on it, if you're not moving, your chair is not going to magically start to roll away. You're going to have to push it. Right? On the same idea, if your chair is rolling, it's going to keep rolling straight. It's not going to magically turn hard to the right. Right? You would have to push it to the right. If your car slows down, right, your body keeps moving. That's inertia, and you push into your seatbelt. That's why you need to wear a seatbelt in a car, because your body wants to keep moving. If you were to get in an accident, you would keep moving in the same straight direction, and you would go flying out of the car. That would be very bad. If the car turns sharply, right, you're not moving in the same straight direction anymore. Your body keeps moving straight ahead, so you feel pushed into the side of the car. So if you've ever played a backseat game of Jello, you may not call it a different thing, where you slam the other people into the sides of the car. Right? Same idea, right? You kind of get pushed to the side, or if you're on a roller coaster that turns sharply, you feel yourself pushed to the outside. That's because you have inertia. You want to keep going straight, but then the car gets in the way. So when we combine these two things together, we get an orbit. All right? So here's the sun, here's the Earth. The Earth wants to keep moving straight to the side. All right? Straight. This is at a 90-degree angle, a right angle. So Earth wants to keep going that way. Gravity wants to pull the Earth straight into the sun. So this combination, since the Earth is trying to go this way, the sun's gravity won't let it, and it ends up moving in a circular path. And in fact, it is in a perfectly continuous orbit, and it stays the same all the time. All right, so gravity and inertia. All right, so these two things combine, and inertia combine to create orbit. All right, so the inertia wants to keep moving straight. Right, but gravity wants to pull into the sun. Right, the combination results in orbit. All right, and you can see the same idea is true for the moon. The moon is trying to go this way. The Earth's gravity is trying to pull it straight into the Earth, and so the resulting combination is an orbital path. All right, so you might want to draw one of these diagrams in their notes too. That's probably going to be pretty helpful. So you don't need to take notes on this slide, but this is kind of cool. We'll talk about this in class tomorrow. The same principle applies to satellites and space stations that are around the Earth. If you are in the space station, you are still being pulled on by Earth's gravity, right? There is gravity in outer space, all right? Despite everything you've been told so far, there is gravity in space. Earth is still pulling you in, but your sideways inertia is so fast that you are essentially constantly falling around the Earth. Gravity tries to pull you in, but you move sideways so fast that you never hit. So imagine this giant cannon launches something. If it doesn't shoot it too hard, gravity pulls it in. But if it's going sideways fast enough, path C right here, it keeps going around forever. Right? And it never slows down and hits. All right? And you end up feeling weightless the same way you feel weightless when falling downhill on a roller coaster. The exception is, if you're on a space station, you're essentially falling down that hill forever, around and around and around. So make sure you write a summary at the bottom. We'll do some cool demos and labs on this in class tomorrow, and I will see you then.